In this video, we're going to look at the sum and difference rule for derivatives. So first thing, what is the sum and difference rule? And basically, in an English sentence, the sum and difference rule says this. The derivative of a sum or difference is equal to the sum or difference of the derivatives. Now, what I like to tell my students is the sum and difference rule for derivatives does exactly what we want it to do for derivatives, which is not necessarily the case for other things like the product rule, the quotient rule, the chain rule, which are a little bit different. So in algebraic notation here, the derivative with respect to x of a sum of two functions, f of x plus g of x, is equal to the derivative of f of x plus the derivative of g of x. And similarly, the derivative with respect to x of f of x minus g of x, the derivative of the difference, is equal to the derivative with respect to x of f of x minus the derivative with respect to x of g of x. Okay, I'm going to show proof for these. If you want to skip over that proof, don't think you need it. You can see in the description there will be a link to the example. Feel free to skip to that. But for the rest of us, it is important to understand why things are true. So let's first prove the sum rule. And so, proof. I'm going to start on one side of this. I'll start on this side, even though it doesn't matter which side. And basically I'm going to start from the derivative with respect to x of f of x plus g of x. And I want to somehow get this, show that this is equal to that. So I'll use the definition of derivatives here and say, okay, the derivative will equal the limit as h approaches 0 of the difference quotient, which is going to be f of x plus h plus g of x plus h minus f of x plus g of x all over h. And now the idea is I know I want to make this look like that, and in order to do that I'm going to separate the f's, and so I will have in this fraction an f of x plus h minus f of x, and separate the g's, so I have a plus g of x plus h minus g of x, and I have this limit as h approaches 0. And what happens here is the following. I can split this up as the two limits, so I can look at the limit of the f's over h, so the limit as h approaches 0 of f of x plus h minus f of x all over h, and the g's, so plus the limit as h approaches 0 of g of x plus h minus g of x all over h. And I know that this here is the limit of the difference quotient of f of x. So that is the derivative with respect to x of f of x. This here is the limit of the difference quotient of g of x. So that is the derivative with respect to x of g of x. And as you can see, by going back to the limit of the difference quotient, I can show that this left-hand side equals this right-hand side, and so I have proven this QED, quod erat demonstrandum, as was to be shown. All right, now the difference rule. So the proof is almost identical. I could use a constant multiple and just use the sum rule for this and say that I have the derivative of f of x plus the derivative of negative g of x and get that out. But I'll just do the same thing over again. So start from one side, so proof. And if you got the last proof, feel free to skip this one. It's going to be almost identical. If you had trouble with the last one, maybe watch this. So I'll start with one side. It doesn't matter which side I start with, but I'm going to start with this side. I usually like starting with the more compact side. I find it easier oftentimes to spread something out than I find necessarily to figure out how it collapses down. But we'll see what happens. So in this one, I'll start from the left-hand side. I know that the derivative with respect to x of f of x minus g of x will equal the limit as h approaches 0 of the difference quotient, f of x plus h minus g of x plus h minus f of x minus g of x all over h. And just like before, my target is to get the derivative of f and the derivative of g out of here, so I will split it up, and I'll take the two f terms, so I have f of x plus h minus f of x. So f of x plus h minus f of x. And I have a negative g of x plus h minus a negative g of x, which is going to get me negative g of x plus h plus g of x. And I still, of course, have the limit. And this is all divided by h. And so now I'm going to split it up. And as I split it up, so I'll have the f terms. So I have the limit as h approaches 0 of f of x plus h minus f of x all over h. And in here, I'm going to factor out a negative sign, so minus the limit as h approaches 0 of, and when I factor it out, this term will now be positive, g of x plus h. This one will be negative, minus g of x all over h. And we can clearly see this right here is the derivative of f of x. So I have the derivative with respect to x of f of x. And then I have a minus. And this right here is the derivative of g of x. So the derivative with respect to x of g of x. And lo and behold, I was able to start on this side and work my way over to that side. So this is proven, as was to be shown. Okay, finally an example, and I'll explain verbally all the bits and pieces, but I'll show the type of work that I might actually show in here. So for this, the first thing I'm going to do is rewrite these two terms in a way that will be easier for me to take the derivative. I do not like how some people do it where they'll take the derivative of this part, it's so easy, and then do some more steps. I want to keep everything valid as I go. So this will equal the derivative with respect to x of 2x cubed minus, I'll rewrite the third root of x as x to the 1 over 3 power. And that works for any root. The fourth root is 1 over 4. The square root is 1 over 2 for the exponent. And I'll rewrite this with a negative exponent. So the 5 and the 3 have an exponent of 1. They don't move, so I have 5/3. But I'll have x to the negative 6th. And now I can just use the power rule that we saw in the previous video. So since I have difference and a sum here, minus and a subtract, I can just take the derivative of this part, the derivative of this part, and the derivative of this part, and put the minus and put the plus. So the derivative of this, well, I have 2 times the derivative of x cubed, which is 3x squared, and I have the minus. The derivative of this, I bring the 1/3 out to the front, and I subtract 1 from the exponent. 1/3 minus 1 is -2/3. And this one, I bring the -6 out to the front, so I have plus 5/3 times -6. And then I have x. I subtract 1 from here, so -6 minus 1 is -7. And let me clean this up some. So I have 6x squared. I will send this x with a negative exponent to the denominator, so I have minus 1 over 3x to the 2/3. And in here, whenever I multiply an integer to a fraction, I multiply it to the numerator because this -6 is -6 over 1. So I will get a minus 6 times 5 is 30, so 30 over 3. And I will send the x to the 7th to the bottom because it was a negative exponent. And one last thing, this fraction here reduces, so my final answer is going to be 6x squared minus 1 over 3x to the 2/3 minus 10 over x to the 7. All right, comment below if you do have any questions. I hope this helped you out.